All right, this video is going to introduce you to binomial experiments and how we verify whether or not a situation is binomial. So the first verification that you would need to look at is whether or not there's a fixed number of trials. So you'll be given some kind of n, and these trials are repetitions of the experiment that's going on. There's also only two possible outcomes, success and failure. We're going to say that that's letter P, and Q is going to end up what we call failure, and so Q must be 1 minus P. It must be the complement of P. It also must be true that the trials are independent under identical conditions. So when trials are independent, if you have anything that is done without replacement, you need to be very clear that like the probability resets every single time. If you have a very small sample, such that when you take one person out of being chosen and that changes your n, so changes, that's the symbol for changes your n, then that would be a without replacement situation, and that would not be independent. All right, we say that if it is a binomial experiment, that we have a binomial probability distribution, and we let capital X be the number of successes in the little n trials. And so this is going to be our notation that we use.
Here's what I found.
So big X is a random variable that is approximated with the normal distribution. Little n is the number of trials, and little p is the probability of success. So here's an example I was giving you of not binomial in a little bit more detail. So if you have some kind of college that's looking for a student advisory committee and you have 10 staff members and 6 students, okay? That means so a total of 16. Now you're going to pull one of these people out of the box. Now what happens is then you have the names, right, still left in there. Well, once you take that person out, you're now only taking out of 15, and so on and so forth. And 1 out of 16, or 6 out of 16 here, and 5 out of 15, those two fractions aren't close enough to say that the probability resets. So that's going to violate the condition of independence, and that's not going to be something that we can look at. Okay, we'll talk more in class about when n is really large, that without replacement doesn't matter, but for the context of this situation, if n is really small, such that when you take somebody out, okay, of the pool that you're choosing from, that it changes the denominator, then we say that those are not independent events. All right, so let's verify why this situation here about developing pancreatic cancer is a binomial experiment. So the first thing it gives us is that the risk of developing pancreatic cancer is going to be consistent. So our probability in this case is 1 out of 78. And so that's a long run frequency that for all pancreatic cancer that we know that. Since that probability of success is stated and remains the same, I know, so I either have success, I should write this, is cancer, and failure is not cancer. Now I know that seems really weird because it's like backwards of what it should be, but that's what we are given here. So the probability of success is cancer, failure not cancer. So that second condition is met here. Also, since this probability remains the same, for all people. Independence can be assumed. Okay, so that means that condition number 3 is met. Now, the last thing is it says, suppose we randomly sample 200 people. So that means that our N is set. And I want to know in that group of 200 people, okay, how many of them are going to develop pancreatic cancer? So out of this 200, condition 1 is met. That is a fixed N.